Hi class, today we are going to go over the next important section, which is linear independence. So I said on the last video that span was very important and it kind of permeates throughout the course. The same thing is true with linear independence. Honestly, linear independence and span kind of go together quite a bit. When you have both things, it's some very important results come out of that, right? So we're always interested in the span of a set and the linear independence of a set. It's something that we're gonna talk about quite often. So let's go ahead and start with the definition. If you have a set of m vectors that have n real components each, okay, then that set of vectors is linearly independent if the only solution to the linear combination of those vectors is, when it's equal to 0, is what we call the trivial solution. Okay, so if I put these together in a linear combination and I say it needs to be equal to 0, if the only solution to that equation or that system of equations is the trivial equation, is the trivial solution, which we define as having everything equal to 0, right? That's the easiest way to make everything 0 or to come out with zeros along my vectors is to have each of these x1, xi terms be 0. That's the easiest way, right? Again, I talked about it a little bit in a previous video, but it's called the trivial solution because it doesn't give us anything interesting out. We can't use it too much. We can use it to define things and to talk about our system, but it doesn't tell us anything about the solution of our system. Okay, so if there are non-trivial solutions, then we call our system linearly dependent. Okay, linearly dependent, so non-trivial solutions. So what we mean by non-trivial solutions is that there are free variables present. Okay, so if there are non-trivial solutions present in the augmented matrix when we reduce it down into echelon form, then that means we have a linearly dependent system. Okay, so let's look at an example. So let's consider the augmented matrix for this system of equations. So again, notice that everything is set equal to 0 here. Each equation equals 0. Our right hand side does not have any values. It's equal to the 0 vector. If we reduce this down into row echelon form, okay, notice that there are no free variables. Each row, okay, each column has a pivot position. Pivot position, pivot position, pivot position. There's no free variables here. So we would classify this as a linearly independent set of vectors. This vector and this vector and this vector are linearly independent of each other. Again, what that means is I could not make this vector by creating a linear combination of these two vectors. I could not create this vector by making a linear combination of these two vectors. I could not create this vector by creating a linear combination of these vectors. Okay, they're all independent of each other. They cannot be created by any of the other ones. And I know that because when I reduce this down to echelon form, all of my vectors, all of my column vectors have a pivot position in them. Okay, there are no free variables present. So the system is linearly independent since there are no free variables. So here, if I were to reduce this down all the way to reduced row echelon form, I would get out that x1 and x2 and x3 are all equal to 0. Okay, they're all equal to 0. In fact, here 6x3 is 0. That means x3 has to be 0. And as I go my backward substitution, we would come to the same conclusion. But again, we prefer to put these into reduced row echelon forms, right? So if I reduce this all the way down, I have my pivots here, okay, along my main diagonal. These remain as 0. There's no free variables anywhere. My solution is the trivial solution. Everything is equal to 0. Okay. X1 is 0, X2 is 0, X3 is 0. Therefore, the trivial solution, x equals 0, 0, 0, is the only solution. Therefore, this system is linearly independent. Okay. Let's take another example. Let's take this system. So notice that I have 4 variables and 3 equations. Right? So I'm kind of missing an equation here. No matter what happens here, I'm going to end up with a free variable. If I get pivot positions along my main diagonal, I'm still going to get a free variable. Right? If this is a pivot and this is a pivot, let's say this is a pivot, I'm going to end up still with a free variable. Right? So no matter what, I don't have enough equations to find all of my solutions. I have to have a free variable. We'll introduce that as a theorem a little bit later on. But if I reduce this down to row echelon form, not reduced row, that's why there's not ones here. Right? I just need to find so that I have an entry with zeros below it so that it's in row echelon form. We'll talk about this in just a second, that there are basically infinite forms for my row echelon form, but only one unique form for my reduced row echelon form. Okay, so that's why there's not ones here. So don't get caught up on that. So since every column vector here does not have a pivot position, there's a free variable. That means that x4 is a free variable, and my system is therefore linearly dependent. Okay, so know that the REF forms are not unique, so the row echelon forms are not unique. If I wanted to show you guys a few of the equivalent row echelon forms for the above matrix, I could do something like divide this entire row by 1. Divide it by 2. And then I'll have a 1, a 2, and a 1 here, but it's still in echelon form because under the pivot positions are all zeros. That's the definition for echelon form, is everywhere you have a pivot or a leading variable, you have zeros under it. That's it for row echelon. Reduced row echelon, you have ones along your pivot positions, zeros below, and zeros above. Right? That is a unique form. REF forms are not unique. Okay, so again here I could have divided this first row by 2, divided the second row by -2, and this last equation by 4. Right? This is an equivalent form to this. Right? It represents the same matrix. All I did was divide everything. I used a elementary row operation. It's still in row echelon form. Okay. I could have divided this by 1, this by -10, and this by 4, and had ones everywhere, and that would have been unique, right? Just like this, right? This is also row echelon form. Okay, so we can use back substitution to find the general form of our dependent solution here, but remember, it's always easier to reduce all the way to reduced row echelon form, because if I do back substitution, I have x3 is -1/4 x4, and then I gotta plug that into here and do some extra work that I'm not gonna enjoy. So my reduced row echelon forms are unique, and they always give me my exact solution. So if we do our reduced row echelon form, it brings me exactly to my solution. So notice that my x1, x2, and x3, they're all in terms of this free variable. Right? Here I would have had to do a lot of extra work after doing this work in order to solve, which is fine if that's your thing. So here we come to the conclusion that x4 is my free variable, x3 is -1/4 x4, and x2 is also -1/4 x4, and x1 is -1/2 x4. Okay, because remember, we have to move this to the other side of the equal sign. So therefore my general solution, my vector solution x, right, is negative 1/2 x4 is x1, my x2, my x3, and then that free variable x4. Okay. We can also write it as a column vector, pull out that x4 term, because remember it can be whatever it wants, and then this is what my vector solution looks like. Okay. So let's come to a theorem. If we have more variables, okay, so that means more columns than we do equations. So there's more columns than there are rows. Our system will be linearly dependent always. So that's what happened here. I had more variables than I had equations, and I came out with a free variable. That will always be true. It's in my theorem. Remember, theorems go if, then. If this is true, then this is true. Okay, if I have more variables than equations, then the system will be linearly dependent. All theorems work in an if-then sort of fashion. So I just want to bring that to your attention. Here's another theorem. If I have m vectors that have n elements each, and m is larger than m, so this is my if condition. Okay, I'm basically saying that I have more variables than equations. M is my number of vectors, my number of variables. N is my number of equations, more variables than equations. Then my set of vectors is linearly dependent. So I'm taking this theorem and I'm really just rewriting it in a term where we are now looking at it in terms of vectors rather than looking at it in terms of equations and variables. Okay, this is for a system. This is for me looking at matrices and vectors, right? If I have more columns than I do rows, I have a linearly dependent system. If I have more variables than equations, I have a linearly dependent system. So they're equivalent theorems, but they're different theorems because one applies to something different than the other. Okay. So example. Now we'll talk about these just in terms of vectors rather than in terms of equations like we did previously, right? Remember, this as an augmented matrix represents a system of equations. So since this theorem represents vectors, we'll talk about in terms of vectors, right? So I have a set of vectors, 1, 2, 3, 4. Okay, so 4 vectors, and each of these vectors are in R3. 1, 2, right? 1, 2, 3. So I have 4 vectors in R3. So this set is going to be linearly dependent. I have more vectors than I do components inside of the vectors. I have 4 vectors in R3. 4 vectors and 3 variables. So the set is linearly dependent due to the previous theorem. Okay. One of these vectors can be written as a linear combination of the others. And now when I say this, you're probably saying, oh yeah, this one can be written as a combination of these because what? These are unit vectors for R3. If I multiply this times 2, multiply this times 3, multiply this times 4, and add them together, I will get this vector. So you see how linear independence and spanning sets go together. If I have a vector that is in my spanning sets, right, if it can be generated by my spanning set, then that'll give me a linearly dependent set of vectors. Okay, so here I have a set of vectors. If I took this one out now and I had just these 3, they would be linearly independent. Okay, now I said that this is the most obvious case. Now what happens if we have this but I took out, let's say, this one? Can I create this vector as a linear combination of this vector, and this vector? The answer is yes. Okay, so this vector would be in the span of these other 3. Right? So if I actually took out any one vector, my set would then be linearly independent in this case. Okay, because I have one too many vectors. So let me reiterate that. Okay, that's because these are unit vectors. It is very, very possible that I have three vectors in 3 space, but they are not linearly independent. Okay, this is just a guaranteed condition for having linear dependence. Right? You might want to rewind that back and write that down in your lecture notes that you are writing as I talk, because that's kind of important. Okay, so again, what I said was it is possible to have 3 vectors in R3 and still have them be linearly dependent, right? This theorem here just guarantees that I have a linearly dependent set, right? If I have more vectors than I have components in the vectors, it's guaranteed that set is linearly dependent, okay? So we'll see all this in examples, okay? I know I'm saying a lot. I'm kind of basically just giving you a preview of what you're going to see later on in the video anyways. So, theorem. For this set of m vectors with n components each, if my set of vectors that I have here is linearly dependent, then there exists a vector which we'll call u sub I. So this little notation I'm going to show you here means there exists, okay, this backwards e means there exists. So there exists a vector inside of this set of vectors such that that vector is a linear combination of the remaining vectors of the set. That's basically what I was trying to talk about here. Okay, this vector, this is a linearly dependent set, right? If I have a set of vectors that are linearly dependent, like I do here, there exists a vector, in this case I chose this one, such that I can write that vector as a linear combination of the remaining vectors of the set. I can take this vector and I can write it as a linear combination of these vectors. That was the obvious example. And I also said I can take, let's say, this vector and I can write it as a linear combination of these 3 vectors. Okay, I can literally take any one of these vectors out and write it as a linear combination of the remaining vectors. It is not, sometimes it's specific to a certain vector, most of the times it's not. Most of the time you can really grab any one vector out and write it as a linear combination of the others. Okay, so there exists not a unique vector, there is just any one vector, or it actually could be a set of vectors that you can pull out and write as a linear combination of the remaining vectors in the set. Okay. So, i.e., another way of saying that, one of the vectors is in the span of the other vectors. This vector is in the span of these 3 vectors. This vector is in the span of these 3 vectors. This vector is in the span of these 3 vectors. This vector is in the span of these 3 vectors. Okay, that's what we're saying here, right? In a linear algebra manner of saying it, that's what we mean. i.e., u sub I is in the span of all of the other vectors where you remove that u sub I. So if you notice, I count all the way up to 1 less than ui, and my very next vector is 1 more than ui, so I'm basically skipping that vector that I pulled out all the way up to um. Okay, so I remove that vector from the set. I can then generate that vector by making a linear combination of the vectors that remain. Okay, or another way of saying that, u sub I can be made as a linear combination. So all I'm doing here is showing you that I'm multiplying each vector by a scalar value, right? This ui minus 1 times an xi minus 1. This ui plus 1 times an xi plus 1. The u sub I is completely skipped here. And that will equal my u sub I, right? So in the previous example, this one that I've revisited quite a few times, any one of the vectors can be written as a linear combination of those that remain. Okay. theorem. Let u1, u2, um in Rn. So again, I have m vectors, and each of these m vectors has n components. And let's make a matrix out of these. Okay, so I have a column vector. First column vector is u1, second column vector is u2, all the way to um. Let this be equivalent to b, where b is in echelon form. Okay, so a and b are equivalent. That does not mean they are the same. B does not equal a. It's saying I'm taking a, and then I reduce it down to echelon form. That echelon form I'm calling b, because it is a different matrix, right? It's not the same matrix, but it is equivalent in that it generates the same space. If I look at the span of the vectors, if A is linearly independent, B is linearly independent, they have the same solution space, right? There's a lot of things. They are equivalent in a lot of ways, although they do not look the same. Okay, so again, I'm giving you a lot of information about things that we're going to talk about in depth, several chapters ahead right now. Okay, so let's just talk about this A matrix and the echelon form of A, which we are calling B. Okay, the span of the column vectors of A is equal to Rn, right? It generates the entire space if the echelon form of A has a pivot position in every row. Okay, every row. The set of vectors u1 up through um is linearly independent if B has a pivot position in every column. So to check for linear independence, we're looking along the column for a pivot position in every column. If there's a pivot position in every row, then I have a spanning set of vectors. Okay, so spanning set of vectors, I'm looking for pivot positions in the rows. For linear independence, I'm looking for pivot positions in the columns. Okay, so let's do an example. Let's call this A. Okay, I have 4 column vectors, 3 equations. When I reduce this down, I have a pivot position in this row, pivot position in this row, and a pivot position in this row. Right? And since each row has a pivot position, that means that those 3 vectors, that all these vectors span R3. I can make any vector in R3 by these 3 vectors. But since each row, this column does not have a pivot position, there's a free variable here, it's not linearly independent. So it spans R3, but it is not linearly independent set of vectors. Okay, which makes sense because again, I'm in R3 and I have more vectors than I need to create R3. Right? So since I have more vectors than I need, I'm going to be linearly dependent. So this is, each of these vectors is it creates a spanning set, but it is also a linearly dependent spanning set. One of these vectors, actually any of these vectors can be created as a linear combination of the remaining vectors, as we saw in the theorem before. Okay, so I've kind of been repeating myself a lot as I do. There's 3 things that are super important that keep coming up over and over again in this section, and they go together very, very well. And that is span, linear combination, and linear independence. Those 3 things are related to each other, and it's very, very important to understand how they're related and how they work together in the system, right? So again, this is a spanning set, okay, because I can generate all of R3, right? All of these are in R3. I can generate all of R3, so it's a spanning set. They are linearly independent because I have too many vectors, which is fine, which means that they are, I can take one of these vectors, any one of these vectors, and write them as a linear combination of the remaining vectors. So that's how span, linear independence, and linear combination kind of flow together, okay, with this example in particular. So to reiterate, the vectors, we're looking at the column vectors now, right? So U1, U2, U3, U4, they span R3. Since each row in my B, my row echelon form, has a pivot position. Pivot position here. Come to the next equation, the next row. I come in, it has a pivot position. It's not all zeros, right? Come into my next row, it has a pivot position also. So this is a spanning set, okay? Each row in B has a leading variable or a pivot position. Pivot position, leading variable, same thing. Remember, I told you I'll go back and forth between that verbiage. So the vectors are linearly dependent since each column in B does not have a pivot. Pivot in this column, pivot here, does not have a pivot, has a pivot. There's a free variable, okay? So suppose we have a matrix equation, AX equals B, not this B, right? A column vector B, our right-hand side equation, where B is not 0. Okay, so here I'm not allowing 0 to be I'm not allowing B to be the 0 vector. Then we call AX equal to 0, right? So if I take B away and I replace it with the 0 vector, this new equation where all I changed was the right-hand side, we call it the associated homogeneous linear system. This happens very, very often and is very, very important in differential equations. Okay, in fact, if you're taking a differential equations course at the same time, you're going to study this very soon if you have not already. Okay, so we call this the associated homogeneous linear system. Okay, in DiffEq, this would be the associated homogeneous linear equation. Okay, the solution to our original AX equals B is called a particular solution, and we call it X sub P, because remember, X is my solution vector. So X sub P is the particular solution. The solution to AX equals 0 is called the homogeneous solution, okay, which we denote with X sub H, the homogeneous solution. If I add together my particular solution with my homogeneous solution, that is called my general solution. Okay, X sub G, the general solution, is the same as the particular solution plus the homogeneous solution. Now, I will say this. Your solution to the particular solution will look very, very similar to the homogeneous portion. Okay, so what's happening here is I need these two to be linearly independent, so we do not repeat things that are the same for the general solution. You'll see what I mean in the example that we do. Okay, so all solutions to my system AX equals B has this form. So it looks like I forgot to make my vector forms here, so I'll fix that in my write-up. Okay, so let's look at another example. Let's look at the homogeneous system. So if you notice, everything is equal to 0. So when we put this in our augmented matrix, we will have the 0 vector for our right-hand side. Okay. Now if I solve this down to reduce row echelon form, if you notice, there's a free variable. Okay. In fact, there's 2 free variables because I have more variables in equations. So in this case, I actually end up with 2 free variables. Okay. So x4 is free, x3 is 4x4, we move it to the other side, and x2 is also free, and so x1 is based on 2 free variables in this case, right? So that's the homogeneous equation. Now, if I find a particular values from my right-hand side, a B matrix, we can do this over again, okay? So if I take my X sub H, it's going to look like this. Again, you can kind of switch the order. I can put the X2 with this column vector on this side and the X4 on this side. But notice that my X1 has negative 2x4 plus 3x2, right? And so everything that's attached to x4 is in its correct place. x1 has a negative 2x4. x2 doesn't exist with an x4, obviously. x3 has a 4x4, and x4 itself is free, so there's 1 there. For x2, it's the same deal. I have 3 of them in the x1 position. It itself exists, and then x3 and x4 do not have any x2s present, right? So that's how we write this as a linear combination for my homogeneous solution vector. Okay. Now let's say we just throw all 1s on the outside. Again, it can be pretty much any value here. We make our augmented matrix. We put it into reduced row echelon form. And if you notice, I have the exact same free variables, because the things that I did, the elementary row operations to get from here to here, are the same. It's just that now things are happening to my right hand side. Whereas before, when I had all zeros, I'm adding 0 plus 0 and multiplying 0 times some number, and nothing's happening here. It just stays 0. Here, I'm doing the exact same operations, so I get the exact same free variables. It's just that now my right hand side has been reduced to something different. Okay, so again, x4 is free. X3 is going to be 0. Okay, oh, I'm sorry, x3 is negative 1. Move the negative 4 over. Okay, because that's x3 right here. x4 is free, so I have a 0 row. x2 is also free, and x1 is going to be negative 2x4 and 3x2. So I can do the same thing when I put this into my particular solution. I'm going to have, for all of the x4s, right, if x4 goes first, I'll have a negative 2. I'll have a 0 in the 2 position. Then I will have a 4 and another 1. Okay, but if you notice, there's one constant form here, right? None of the others have a constant, so I'm going to have a third vector. You come here, right? I'm just going to have these exact same vectors, but there's going to be an initial vector for the constant terms, because my particular solution will have constant values. So this is the particular solution for this case plus the homogeneous solution. And if I add those together, that is my general solution. And in fact, this solution will work for the homogeneous will work for any system. This will work for this particular b vector that I have. If I have a different b vector, then this x particular solution portion will change as well with this, but this will always be the same, right? Because this is to the homogeneous portion, so then you're including the particular portion to get your generalized solution. So matrix vector multiplication satisfies the distributive property. We're not going to get into multiplying matrices yet. That is going to be for the next section, 3.1. So this is sort of a preemptive thing here to show the properties that it satisfies. But if I have a matrix and I'm multiplying that times an addition of vectors, it's the same thing if I were to distribute the A across to each vector. Okay. Notice here that A is on the left-hand side of the equation of the vectors, and over here A is still on the left-hand side. That's actually very, very important. We'll talk about that a lot in the next video. Okay. Theorem. Suppose we have M vectors in Rn as well as a B vector with n components. Then if one of the following statements that I'm going to show you is true, then all of the statements are true. Okay, or what we like to say equivalent. If one is false, then all of them are false. Okay, so the first thing is that the set of vectors is linearly independent. So if that's true, then so is the vector equation being created by those vectors equaling to B having at most one solution is also true. Okay, so if they're linearly independent, then any vector equation created by those are true as well. The linear system created by those column vectors with B as the right hand side will have at most one solution. Now this should make sense because these two are basically the same thing. One we're looking at as a vector equation, the other as a system of equations in matrix form, augmented matrix form. And here we're looking at it as a matrix equation, saying that it has at most one solution. So these three are really all equivalent ways of looking at the same system of equations. Okay? So this is going to lead us to what we call the big theorem. So this is a theorem that's going to run throughout, let's say, half of the course. Okay, we're going to call it accumulative because as we develop more and more things to work with, we're going to add to this theorem. So basically it's going to work the same way as this. Okay, we're going to have a couple of things that we're going to say is true, and if one of them is true, all of them is true. If one of them is false, then all of them are false. Okay, so it's a big theorem. I think towards the end we're going to have something like 15 different items in this theorem. I think right now we're going to have like 3 or 4, but we're going to accumulate quite a few things into this theorem. It's a really, really big, important theorem, and you'll actually be pretty familiar with it by the time we're done with this class because, again, linear algebra it's difficult because it's different, but a lot of the concepts are there in sort of every single aspect of what it is that we talk about in this class, right? So you see the same things over and over and over again, so you just get used to it. It's not like a regular calculus class where you learn one thing and then the next chapter is something different and the next chapter is something different. Everything combines together in this class. Every single section or chapter builds off of the previous material. Everything just keeps getting, it's really a snowball effect where everything just keeps getting added on and on and on and just becomes this big sort of structure that we're going to talk about. Okay, so let's talk about the big theorem. Okay, so there's some things that we need in order to talk about the items in this theorem. So first of all, let's say that we have a set of vectors, and we'll call this, the set of vectors has n components, and there are also n of these vectors. So these two n's are the same. So there's n vectors with n components. We will call this set of vectors A. Okay, and in fact, this is a fancy A because we're going to have another A where we create a matrix out of these vectors. So we're going to take these n vectors and we're going to create we're going to use them as column vectors to create a matrix. So this will have n columns and n rows. So this will be an n by n matrix. And again, we'll get into matrices in the next video. So then the following of these are equivalent. So again, if one is true, all is true. If one is false, then all of them are false. Or we can say that we can't say anything about the others. Okay. So if A is linearly independent, so if all of these vectors are linearly independent of each other, then A will also span Rn, and that's because there are n vectors in n space. So again, if I had 3 vectors in R3 and they were linearly independent, they would span R3. Okay, so this is how they go together. Very, very important. So if we have n linearly independent vectors in n space, it will span Rn. Right? So they're tied together. For every B that is in Rn, for all B in Rn, so every single right-hand side vector you could ever think of with n components, the matrix equation Ax equals B has a unique solution. Okay, so this is just saying that when we have n vectors with n elements, the augmented matrix is going to be have n rows and n columns, and then you'll have your b column for the augmented side, right, the right hand side. Okay, that's our big theorem. So right now we only have 3. It's very, very similar to what we have here, but this relates linear independence with span and the existence of unique solutions. Okay, again, this is going to grow to like 15 different items. So right now we got it while it's small. Very, very nice. We will expand on this topic. Okay, so let's do a proof. Okay, prove that if u and v are linearly independent vectors, and the set u, v, and w is linearly dependent, then w is in span of u and v. That means that w can be made as a linear combination of u and v. So we talked about this in a theorem. We've talked about it several times. We've had concrete examples, but we have not proven it yet. Now, we've talked about 1 or 2 proofs already. I want to be very clear here. Proofs and examples are not the same thing. If you try to give me as a proof something like this, okay, where, let's go to the different, something like this, right, where these are linearly independent, but all together they're linearly dependent, and then showing me that I can write this as a combination of these, you're showing me an example of this proof that we're trying to do. Okay, now when you do a proof, you are not giving an example, right? I'm not saying, hey, these are independent, but when I add w, now that they're dependent, show me that you can write this as a combination of this, and let me give you an example of that. That's not a proof. A proof is for all cases. If you show me an example, that's one case. Okay. Now, if I were to tell you something like, it rains every single Tuesday, and I take you outside on a Tuesday and it's raining, that doesn't prove that every single Tuesday it rains. It just means that on this Tuesday it happened to be raining. So look at this. Now I proved myself. That's incorrect. And that's what you would be doing in this case if you did something like that. Now, if you took me out every single Tuesday for my entire life and showed me it was raining, then you could prove it to me. But if you just do it once, you just brought me out on a single Tuesday, it happened to be raining. That's not the same thing. Okay? So what we need to do is we need to show this in general. You need to generally show me that this is true. Okay? So you should not have a 1, a 2, a 3, a 28, a 17. You should not have a specific value in your proof at all. It should only be general, abstract, A's, B's, C's, U's, and V's, things like that. U1, U2, U3, those kinds of things in a proof. You should never ever give me an example unless it is a counter example. Okay? You can prove I'm wrong by showing me an example. For instance, if you tell me it rains every single Tuesday and I bring you outside on a Tuesday and it's not raining, I win. I proved you wrong. So you can prove something is incorrect with a counterexample, but you cannot prove me correct with an example. Okay? So, I hope that helps a little bit. Let's go ahead and get started. So again, whenever we have a proof, we have to specify that we're doing a proof. So prove, verify, show, all of those means we are doing a proof. Okay? So again, a proof is a blank slate. There's nothing here, nothing exists. I can't talk about adding u and v if I don't know what u and v are. What is u and v? Are they ants? Are they sandwiches? Are they vectors? Are they matrices? Are they functions? I don't know. So I can't just go, hey, u and v is this. I need to talk about what I have. Okay? So an easy way to is you look at the if part. If I have this stuff, this is what I need to prove, right? I said all theorems are ifs and then thens. Proofs generally work the same way. If I have this, so I'm assuming that that's true, then this is what I can prove to you. So this should be my end conclusion, and these are my assumptions. So I need a u, and I need a v, and I need a w. So let's start with that. Okay, I need u and v to be linearly independent, and I need u, v, and w to be linearly dependent, right? So I have two vectors that are independent, so I'm starting with if, okay? I literally just copied the if line, and then now I'm going to work my way down until I can get down to my event, right? So I got two vectors, they're linearly independent. If I'm adding a third vector, the set of those are now linearly dependent. Then, do you remember what this symbol means? It means that there exists. So there exists an x1, an x2, and an x3 in R such that if I use these as my coefficients, I will get out the 0 vector, okay? And at least one of these cannot be 0, right? Because that's what it means to be linearly dependent, right? So I said what I need, and then I said what that means, okay? U, v, and w linearly dependent. That means that if I write it as a linear combination, and I set it equal to the 0 vector, I cannot have the trivial solution. I have to have a non-trivial solution. That means this and this can be 0, but this one can't. Or maybe this one and this one can be 0, but this one can't. One of these cannot be 0. Because if they're all 0, then that means I have the trivial solution. If I have the trivial solution, that means they're linearly independent, which is false. So this is what I'm doing. I said I have a linearly dependent set, so I write the definition of what it means to be linearly dependent. Okay. So note that if x3 happens to be 0, then either this one has to be 0 or not 0, or x2 has to be not 0. Okay. So if I let this one be 0, that means one of these is not 0. If I'm saying this is the 0 one. Because remember, one of them has to not be 0. Okay. At minimum. If I had two zeros and one not 0. So if that's true, then this, which I know is linearly independent, right, does not have the trivial solution. Because again, what does it mean to have the trivial solution? Trivial solution means that the only way for this to be true is if this is 0 and this is 0. Okay? So if I say, hey, let this be one that's 0, then that means one of these has to be not 0 because it's dependent. That goes against what I know is true, right? I know that these are independent. So there's no way that one of these things cannot be 0. They have to be 0 because they're independent, which means the trivial solution is the only solution here. Okay? It's a contradiction because u and v are linearly independent, right? Therefore, that means that this is the one that's not 0, right? So that means that x1 times u plus x2 times v plus x3 w equaling 0 implies that w can be written in this form. Okay? So that means that, remember, x3 is the one that's not 0, right? So if I solve for w, so I subtract this, divide everything by x3, that's what w looks like. Okay? What's x1 over x3? I don't know because it's not, remember, not an example. But remember, x1, x2, and x3 are constants. x3 is not 0. A constant over a constant is a constant. Constant over a constant is a constant. So what does that mean? This is a constant times u plus another constant times v. It's a linear combination of u and v. Okay? Therefore, w is a linear combination of u and v. Therefore, w is in the span of u and v, because if it's in the span of these vectors, it can be written as a linear combination of those vectors. So this is a little bit more of a difficult proof. This is what we call a proof by contrapositive. We're kind of assuming one thing and saying that's impossible for that to happen, so that this has the only other option in order for it to work. Okay? You're not going to run into a lot of these proofs, but that look like this, but this is a good example for you guys to see. All right. See you guys on the next video when we start to talk about matrices and their arithmetic.